All right, so we want to look at regression analysis. Regression analysis is very broad and has a lot of applications in a lot of fields and a lot of areas, and it is something that has been widely used, a technique that has been widely used, and mostly it's used to predict the value of what we call a dependent variable based on the value of at least one independent variable. If you remember what I said in correlation analysis, we mentioned that one of the things about correlation is that you cannot use correlation to predict. It just tells you that there's a relationship, but it doesn't tell you that, give you the ability to predict the value of one variable using the other. Okay, so let's take for example, you have, let's say, a business math, and then you have a quantitative method score, and you happened to be one who didn't maybe undertake a quantitative methods test. But we found out that there is a relationship between a business math score and then your quantitative method score. Once we find out that there is a very substantial relationship between them, we can use the business math score to predict what you would have obtained if you had written the quantitative method. You get it? So if business math and quant are positively correlated, then it means that if you scored low in business math, chances are that you would by all means score low in the quantitative method. If you scored high in business math, chances are that you would have perhaps scored a higher mark in quantitative method. And also, we if the relationships are negative. Okay, can you hear me? If your relationships are negative, then it means that if you scored low in business math, then chances are that you would score high in quantitative methods. So yeah, those are the dynamics that we have in here. So we are going to use this technique to help us provide or to predict the value of one variable based on the value of at least another variable. Okay, so we are going to differentiate between our variables. We have what we call, and then we're also going to explain the impact of changes in one variable, okay, in an independent variable on the dependent variable. So if an independent variable changes, what is the corresponding impact on the dependent variable, basically. Now, we've learned two things: a dependent variable and independent variable. What are they? Now, a dependent variable is the variable that you wish to explain, okay, the one you wish to predict. So if I want to use um, your business math score to predict your quantitative method score, then we are making a statement that your quant score depends highly on your business math score. Okay, so in this case, your quantitative method score becomes your dependent variable, and then your business math score becomes your independent variable. The independent variable is used to explain the dependent variable, basically. Okay, and you can, in some books they call it the predictor variable. Okay, because it is being used to predict another value of a variable. Very good. Now, there are various types of regression models, and these types occur depending on the kind of relationship or the kind of model that we want to build. So we can have the linear relationships, okay, the linear models. like the ones we have here. It can be negative or it can be positive. But we can also have a non-linear kind of model. Okay, we are not going to worry ourselves with the non-linear models. Maybe when you grow up, you learn more about these later in life. Okay, but you would concern ourselves with these linear regression models and see how they are done. Also, we are going to concern ourselves with what we call a simple linear regression model. We can have a multiple linear regression model where there are several independent variables and then there is only one dependent variable. And practically, if you really want to predict, okay, we need several predictor variables in order to predict an unknown value of a dependent variable. Okay, but what we are going to do today and for now is basically we're going to use only one independent variable to predict the dependent variable, and we are going to call it the simple linear regression model. Okay. Perhaps next semester, when you guys are doing your research methods, you would undertake some practical examples and you would be doing more of multiple linear regression models, right? Which is more fun than the simple linear regression model. So that is it. We will be dealing with one dependent variable and then one independent variable. Okay, and these are some of the properties that you're going to see that the relationship between the x, which we are going to call the dependent variable, and y, sorry, x, which is the independent variable, and y, which is the dependent variable, is described by a certain linear function. Okay, and changes in y are assumed to be caused by changes in x. All right. Okay, so we can't do regression without math, right? There is a model that you would specify. Okay, and this is the general form of a linear regression model where you have an equation or a relation that expresses y, which is the dependent variable, in terms of x, which is the independent variable. Okay, so if you remember your equation of a straight line, we used to say that y is equal to mx plus c, where m is the slope and c is the y-intercept. And then, of course, the y and then the x variables are shown in the equation. Think of a linear regression model as a straight line. Okay, as a simple equation of a straight line with a slope and an intercept. Just that now we've added what we call an error term. Okay, we've added the error term to it. Okay, so what are we saying concerning this? What we are saying is that the model is giving us this. Y is equal to beta naught plus beta 1 x plus epsilon, where epsilon is the error term. Okay, beta naught is like the y-intercept in the equation of a straight line. Okay, beta 1 is like the slope in the equation of a straight line, and then the new addition is the error term. Okay, now why do we have to add the error term in a linear model of this nature? Because we are using x to predict y. Okay, and if we are using x to predict y, then what it really means is that we will just predict, and chances are that the actual value of y may not be the same as the predicted value of y. Okay, The fact that I'm able to predict your quantitative method score doesn't mean that I will get it accurately. Perhaps I will get a value that is close to your actual score, but I may not get the accurate score. Okay, so what the difference between the actual and then the predictor is measured with the error. Okay, so that is basically why we have the error as part of the model. So this is what we have, and this part is the linear component, and then this part is the error term. So your dependent variable y, your intercept is beta naught, the slope, that is the coefficient, is beta 1, your independent variable is x, and then we have the random term or the residual. Okay, now these are some assumptions that we are going to use and in regression model, and these assumptions should hold anytime we are doing such a model. So number one, your error terms are statistically independent of each other. Your error values are normally distributed. The population of errors, probability of distribution of errors is also normal. Probability distribution of the error has a constant variance. And then the underlying relationship between x and y is linear. And yes, we are typically going to deal with a linear regression. So the last assumption is a very important assumption for us. Okay, in 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 when we're doing this scatter plot, okay, um, there were several ways that the scatter plot could have even helped us to, as it were, provide an equation, okay, linear equation. And this would have been better if we drew a line of best fit into the point, right? And based on that line of best fit, we could have calculated the slope and then the intercept and all that. Okay. But that line of best fit, because we are drawing it with our eye, it's prone to quite a number of errors, and also different people would have different lines for the same data, right? So we have an approach that helps us, and that approach is what we are doing as the simple linear regression. Now, basically, what this entails, remember I told you that we are going to predict. Okay, what this entails is that we are going to draw a line through the um, the set of equations that we have. Okay, sorry, the set of values, the scatter plots that we have plotted, and we want to draw the line in such a way that the errors that um that you see between the actual and then the predicted is minimized. Remember that for this point, okay, this is our predicted value, but this is the actual value. So that space there measures the error. For this point, this is the predicted, but this is the actual. So there's an error here. The same thing, there's an error here, and then there's an error, and then this one is quite close. Okay, so for for every point, there is a difference between the predicted and then the actual. Okay, now we want to draw a line that passes through these points in such a way that these error terms are minimized. Okay, because the smaller the error terms, the more accurate our estimation becomes. Okay, so we want to minimize our error terms. So when you draw the line, you see that we have the slope. The slope is what is measured with B1, and then the intercept is what is measured in as B0. Then the error is what we see here. Okay, now when you use the this line, okay, to predict this equation, this parent equation, then you have an estimated regression model. So this model here is the population regression model, like the specified regression model. Okay. Now, when we get our data and then we begin to do our estimation, then we obtain an estimated regression model, a line that provides an estimate of the population regression line. Okay, and basically what we are saying is that we've used the sample data to estimate the population data. Okay, and in that form, we, because an estimate, we are not going to have the error term, and it's just going to be y hat. Okay, there's a cap on the y, to show that it is the estimated y value, and then there's an estimated regression intercept, and then there's an estimated value of b1, which is the slope. So beta naught here has been estimated with b0, and then beta 1 here has been estimated with what, b1, basically. All right. So as I mentioned, we are interested in minimizing the errors. Okay, we are interested in minimizing the errors. So in obtaining B0 and B1, we obtain them in such a way that the errors that we have is minimized. Okay, so the B0 and B1 are obtained by finding values such that they minimize the sum of squared residuals, or the sum of squared errors. Okay, so you see that the error is the same as the difference between the actual y and the predicted y. Okay, and of course, this predicted y can be expressed as that, right? This predicted y can be expressed as this, as in when we know what this y, predicted y, is. So it's just about putting the value in there. Okay, and there's some calculus involved in doing this, in trying to obtain beta 0 and beta 1 that minimizes our error terms. We are not going to go through that calculus, but you're going to use the results, okay, that is derived out of this technique. We call this technique the least square criterion. Okay, the least squares approach to finding the values of b0 and then b1. Now, once you've been able to find that, you end up getting this. Now, this is very important as far as you are concerned. Okay, in order to estimate beta 1, which is the slope, which we are terming as b1, okay, is the same as summing into x minus x bar, y minus y bar over the summation x minus x bar all squared. And you saw something close to this when you were looking at how to determine the value of the correlation coefficient. It's not the actual relation, but it is close to it, right? Or you can use the algebraic equivalent, which is sigma xy minus summation of x summation of y over n into summation of x squared minus summation of x over n, right? And then the b0, okay, the b0 is expressed as y bar, which is the average, minus b1 into x bar. So you realize that we need b1 to calculate b0. So you try as much as possible to score b1, get b1 correct, so that b0 would also be correct. Okay. Otherwise, you are just going through a downward spiral. Okay. Now, what is very remarkable for us and what is very important for us is our ability to interpret this slope as well as the intercept that we see. Okay. So beta 0, what does it mean? Beta 1, what does it mean? Okay, now the beta 0 or the B0 is the estimated average value of y when the value of x is 0. Okay, sometimes it has a very the interpretive ability, okay, makes sense, but other times too it doesn't make sense in interpreting it. But generally, the B0 is the estimated average value of y when the value of x is 0. And the B1 is the estimated change in the average value as a result of one unit change in x. Okay, so if there's a unit change in the independent variable, what is the corresponding change in the dependent variable? And that is measured with the B1. Very good. Now, how do we find the least squares equation? Okay, the coefficients of B1 and B2, mostly we use if you have a large data set and if you have a lot of independent variables, we have the aid of softwares. Yeah, Microsoft Excel is here again. Other softwares such as Minitab, SPSS, Stata, MATLAB, all of those softwares help us in determining um, the values of B0, B1, B2, B3, and so on and so forth, right? But we are going to concern ourselves with, and because we are going to go mechanical and calculate, we would concern ourselves with quite a relatively smaller sample size, and then um, only one independent variable. Okay, but it's the same approach, that the techniques that they use is the same approach that has been extended to several samples and then several variables. Okay, so other measures, if you generate a computer-based output, you'll be seen to be computed and so on and so forth, right? You'll be doing more of that. This is just an introductory course, and you'll be doing more of that in latter parts of your stay in the university. All right. So let's take an example and bring all that we have said into perspective. Okay. Um, it's easier for us to use an example. A real estate agent wishes to examine the relationship between the selling price of a home and its size, measured in square feet, right? A random sample of 10 houses are selected, and then we have Y, which is the selling price, and then X, which is the size of the house. I think can someone help us in going through this question? If someone can volunteer. Today's the last day, so please you volunteer quickly. All right, so that we close early. Great. Okay. All right, Maureen, please let's continue. Um yep. So can you read for us?
A real estate agent wishes to examine the relationship between the selling price of a home and its size measured in square feet. A random sample of 10 houses is selected.
Okay.
Dependent variable is Y. An
No?
independent
Okay.
variable is it?
Yeah. So they said the dependent variable is the house price. Do you get it?
Yeah.
And then the independent variable is the
Square.
size of the house. The size of the house measured in square feet. Right.
Mhm.
Now, why do you think that the house price is rather the dependent variable? Why don't we why didn't we use the size of the house as a dependent variable? And this question goes to all of you. So if you have any response, you can put it in the chat box. Okay. All right. Why do you think that, based on the question we are having, the dependent variable should be the house price, but not the size of the house?
I think it's the independence variable that is determining the price that the house will be sold for.
Mhm. Okay. Yes. Any other? Yes, Michael. Yeah.
So I think the independent variable was the square feet because, like,
I can hear
once
you.
you build,
Wait.
I think the independence variable was the square feet because once you build the house on it, like, you can't either, like, it becomes fixed unless you want to, maybe some conditions come that you want to extend it. But the price of the house, as price inflation and stuff on the same land, the price of the house can increase. So the price of the house can change as time goes on, whilst the land is fixed.
Okay. All right. I think Foster also mentioned the same thing. Eugenia.
Yeah, sir.
Mm-hmm.
Please, I think the price of the house is dependent. It's a dependent variable because the price depends on the square feet of the house.
On the size
So
of
I
the house.
feel
This is the
of
size.
the size of the house, yeah. So if the house is bigger, the price would also increase, meaning that like the price of the house is dependent on how big the house is.
Okay. All right. All right. Thank you. So yes, generally that's it. But even when you look at the question, the real estate agent wishes to examine the relationship between the selling price of a home and its size. And generally, even if you look at it in a very crude way, without even understanding anything about what dependent and independent variable is, realize that the price is determined by the size. Of course, someone can also look at the price, and then predict the size out of it, right? It can happen, but generally it makes sense that we use the size to predict the price, so that bigger houses may cost more, right? And then smaller houses may cost less. Another question I want to ask: is the size the only determinant for the price of a house?
Oh,
Is size the only determinant for the price of the house? Yeah, Michael.
No, please.
So what other determinants could we have?
To
What other determinants could we have?
that, like, so I don't get your question. You asked whether is the size of the.
So I'm asking whether is the size the only determinant for a price of the house?
mm,
No,
And you said,
no, please.
and I'm saying that
Yes,
what other determinants can we have?
and we can
Mm.
have building materials or the costs for building or something.
And so
Okay.
The location.
Location, yeah, yes, Eugenia.
yeah, I was coming to say the location and sometimes the interior of the house,
Okay,
and yeah,
okay. I think
and the
location.
amenities the house comes with.
Yeah,
So if a house comes with a pool, the price would also increase.
yeah.
Yeah.
All right. Just a minute. Just a minute. So we are saying that the 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 house, the location is a very serious determinant, right? You can have a small house located somewhere in East Legon, and then it's more
Yeah.
expensive than a big house located in another area, right? I don't like mentioning areas. Okay, but there are also other things. Someone talked about the interior, I mean the facilities that are available in the house. Um, someone said the equipment in the house, someone said the cost of the building, someone said the structure, someone said the quality. The quality, I don't know what it means by quality. Are you talking about the quality of material they use to build the house? Yeah, of course, and sometimes yeah, but the size and then the location are very important determinants for 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 a house price, right? And maybe the one who built it isn't it. Of course, that's where the quality comes in.
Yeah.
So, Reggie Manuel or Trasaco or any of these big contractors will build a house, and no matter how small it is, it's quite expensive than maybe a new up and coming contractor who would want to now get into the market to build, right? So there are so many dynamics that comes in when you are determining the price of a house. Okay, that is why when we are predicting only the house price with the size, okay, you'll be prone to some errors because you are not using all the determinants in predicting the price, but you're just using one determinant. You get it? So you would find some appreciable level of error because you've not included all the things that you should include in determining the price of a house. Okay, let's move on. All right, so Eugenia and Maureen, just stay on, okay, so that we can go through this together. Right, we can use Excel to generate regression model output, and as I said, there are so many things that you see in the analysis tool pack in Excel, and you can go through it and familiarize yourself with it. But um, basically, when you do so, it generates an output. I think we can do the Excel bits together. Then we can do the mechanical tasks. Okay, so I'm going to once again uh, permission to use Excel. So we would go through this approach again, and then we'll see. So we have two variables, right? The size of the house and then the price. Okay,
Price.
we have some data. So price and then size.
Square
Okay. And what are the prices? 245, 312, 279, 308, 199, 219, 405, 324, 319, and then 255. And then the
Are you using one? I thought I had one.
okay. Let me see. Oh, I just want to look at the data well, and then okay, that's great. Okay, so we have that, and then we can look at the size, which is our x, right? So we have 1400, 1600, 1700, 1875, 1100, 1550, 2350, 1425, and then 1700. Okay, so I missed something. 14, 16, 17, 1875, 1100, 1550, 2350. There's 2450, which I missed. Uh, okay, so we have that. So 2450 here. So yeah, so we have that available here, and we have the price, and then we have the size of the house. Okay. I don't know what the price is measured in. I think it's measured somewhere. Okay, your place is a bit noisy, so I would, yeah, that's great. So we have that. So you have the price, and then we have the size, and you want to use the Excel first to do or to find a solution, and then when we are done, we would use the mechanical approach to do that. So once you have invoked your analysis two pack, and it's the same way as you would have done when you were invoking solver in linear programming, right? So you when you add that add in, okay, you go to data, and then you choose data analysis. Is located somewhere at the top right corner. So when you choose data analysis, you would see a lot of techniques, right? And over blah 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 and everything. So we choose regression, right? You double click it, or you pick OK. Then it asks you for the Y range. Okay, the Y range is the dependent variable. So we have everything here. Okay, you remember that when I was picking, I picked the label. Okay, I picked the label, I added it. Then I have the input X range. I also pick it, the size. Okay, so I have that. And because the labels are included in the data range that I picked, I have to check this labels box. Okay, then that is all. The other ones you can just ignore them. And okay, good. So it generates a report for you, and we would interpret this report as time goes on, but this is really the Excel generated report. And for now, we will be interested very much in these coefficients, okay, and how they are interpreted, these two, and that is what we have in the reports that we have here, and as the slides will see. So based on these coefficients, okay, the intercept is the value of the B0, okay, and then this one, I indicated it as size, not square feet. And I think size is a more, it's a better description than just square feet. Square feet is just a unit. The size is 0.1097. Okay, the size is 0.1097. That's the coefficient of the size. And then we have the house price. Okay. Now remember that the house price was given in thousands. Okay, so typically this was supposed to be 245,000 and so on and so forth. Okay. All right. We could have drawn a scatter plot to see the value of the to see how the data was arranged. And if you draw a line of best fit, is the line that has an intercept to be 98.248, right? Which is this one, and then a slope of 0.1097, which is that. Okay. So the house price, the predicted house price is what? It's 98 plus 0.10977. Okay. Let's see how we are going to interpret the value of these. And I want you to follow me here. So Maureen, if you are still on, how, based on what we said, as the interpretation of the slope and the intercept, where B0 is the estimated value of Y when the value of X is 0, and B1 is the estimated change in the average value of y as a result of a unit change in x, right? How do we interpret this equation? So how do we interpret, first of all, the 98.2? Yeah.
Okay, it means that for the 98.2, it means if um the square feet is 0,
Let's
the
use,
house price will be 98.2. That's the B0.
so if the house size is 0,
The
right?
size, yes. Yeah.
Okay. The value of the house price would be what? The value of the price of the house would be what?
98.2483.
98.2. About, remember that the house is measured in thousands. You get
Thousands,
it?
yes.
So it's about 98,000.
248.33.
Okay. So if we extend the decimal places, because we are explaining it, you have to ensure that all of those things come to mind, because the unit
Okay.
within the house is being measured, the price is being measured, is in thousands of, I don't know whether it was cities or dollars, but it's in its thousands. So you have to take note of that. Okay, now anybody else to tell me how the slope is interpreted? How is the slope interpreted? Yes, anybody to tell me?
Hello.
Okay, yeah, Maureen, how is the slope interpreted? Nobody
Okay.
wants to help you out. So,
It means on average the prices of the house will increase by 1097.7. That's 1097 as
100.
a result of the unit increase in the size of the house.
Okay. So what we mean to say that all things being equal, right? And on the average, for any unit increase in the size of the house, okay, if the house increases by 1 square foot, okay, the price of the house will increase by how much? 109.7.
Oh, okay.
Do you get it? So
Yeah.
when you are interpreting this, you have to be very careful you do not miss out um, on the size, on the unit within which the equipment is measured. Okay, because that is very important in determining the price of the house. Okay, that is quite important for us. Okay, any question? All right. So what we are saying again is that for any unit increase in the size of the house, the price of the house will increase by this value. Okay. But when you go and check the data, the price of the house is measured in thousands. Okay. So when you are interpreting, you have to also take into consideration that thousands that we are seeing. Okay. So whatever we have here should be in thousands. So if there's a unit increase in the size of the house, okay, that is 1 square foot increase in the size of the house. For every 1 square foot increase in the size of the house, the price of the house is going to increase by not 0.10977, but it's going to increase by $109.77 or cities or whatever unit it is measured in. Okay, that is what I'm saying. All right. Okay, so we have that. Okay. Yes, Junior.
Please, could you please go over uh, back, please go back to the other slide. Yeah, so I want you to go over on the intercept. I mean, how are you going to interpret the intercept?
The intercept said if it's only when this side is 0, right? That's when you get the intercept. So no houses has 0 feet. So your B0 is this. It just indicates that for houses within the range of sizes observed, this is the portion of the house that is not explained by the size. The intercept can be used in measuring, can be measured using a lot of ways, right? But what we are saying is that when the size is 0, this is how the value of the intercept, or this is how the price looks like. Okay. It also tells you that that's the portion of the house price that is not really explained by the size of the house, and is the portion of the price that can be attributable to other other factors such as the location or any other factor that has not been accounted for in the model. Okay, so it doesn't necessarily mean that if there is no size, okay, like we can't have a house without a size. That's what I'm saying, that sometimes the interpretive value you have to be very careful.
Yeah, so I was wondering how
So
I will get 0.
you can't have the size, a house without a size. But it just tells you that, okay, if I'm considering other factors, okay, if I'm considering other factors, it tells you that the other factors can also affect the price of the house. Okay, so all those other factors that has not been able to be explained by the house, okay, will be placed under that intercept. Okay, so when the x is 0, you will see the influence of the other factors in the determinant of the price of the house. I think that is okay, right?
Okay.
Okay. So we move on, and we've been able to explain what the B1 is, and that is it. Um, let's okay, left off. Okay, so we've been able to interpret what these coefficients mean, and interpreting them is very key, especially this one, the beta one. Okay, interpreting it is very key. Okay, so we saw something in ANOVA, SST, SSB, SSW. There's also something like that in regression. Okay, but before we move on, I think it will be good if we learn how to use the not just the Excel in estimating, because if you are, I mean, given an exam, you may not just use Excel, but you may have to do the actual in calculation. So let's do that. Okay, let's see how we would calculate these values, the intercept and then the regression coefficient. Okay, so this is what we are going to use, right? This is what we are going to use. And when we're doing the how do you call it, just hold on a minute. Yep. When we were treating the correlation analysis, there was some thing that we're using a formula that is close to this, right? So I'm going to use that same approach. I'm going to find the beta one, the B1 using this, and then B0 using that. Assuming there's no Excel, it's supposed to work mechanically, right? Okay, so you create another cell. Let's call it X minus X bar, right? And then you have Y minus Y bar, right? And yep. So means that we have to find the average, isn't it? We have to find the average. So let's say average. The average is the average, of course. So the average of all the prices, and then the average of all the house sizes. We have them here. So your X minus X bar is the size, right? The size here, minus the average value, which is 1715. We run it through, and then we find the value of the average. And then the y minus y bar is actually the price minus the average price also. We run it through, and then we get, or we obtain, our y minus y bar. Then of course okay, of course we would also find the product, because the relation says x minus x bar into y minus y bar, right? So we have x minus x bar to y minus y bar. Okay, so that is this multiply that, no, that, then we would run it through, and we are interested in the summation, right? So we are interested in the sum of all the x minus x bar. So we have this, we put it together, and then we sum. Okay, and then we would also have a look at the summation of the x minus x bar all squared. So we have that x minus x bar all squared. So it is this raised to the power 2 that gives us that, and then you run it through. This 0 is not supposed to be there, and then we have that. Okay, so we have everything that we need to solve. So we can now solve for our b1. Our b1 will just be equal to this, right, divided by that, and this is what we got. I think this is the same answer that we got, right? And then we are saying that the b0 is actually y bar minus what? The b1 times the x bar. Okay, we already have the x bar and then the y bar. So this is the y bar and this is the x bar. So you have to find the b0. So we are saying that it is the y bar minus the b1 times the x bar when you are done. So you have that, and you have the same value as we had when we did using the Excel. So mechanically, this is how you do it. You ensure that you have all of these cells, and then if you are doing it mechanical, you may have to bring the tables and then learn how to calculate this. If you are lucky enough and you are giving this average, the summations, then that is cool for you. So you can do it. All right. So okay, let's come back to our explained and then the unexplained variation. Okay, now just as we did in ANOVA, where we said that the sum of squares or the total variation can be explained into two, can be grouped into two. The one that is due to between the groups and the one that is due to within the groups. In the same way, you can have such variations in regression. Now, the total variation can be made up of two parts. The one that is due to error, the one that we cannot explain, okay, and then the one that is due to the regression. So part of the total variation can be explained by the regression, okay, the line that you have drawn, and then part of the variation cannot be explained by the regression. If your model is a good model, okay, then you expect that a lot more of your total variation should be explained by the regression. So if your regression is good, if your model is well fitting, okay, then it means that this SSR, okay, should be way bigger, okay, than this SSE. if the model is not well fitting, okay, and I'm not saying if the model was calculated wrong, if the model is not well fitting. In other words, if house price, the size of a house is not a good predictor of the price of the house, then you would see that it will have a very huge SSE value of unexplained variation than the SSR. Okay, so you are going to learn how to calculate some of these explained and unexplained variations. Now, the total variation is the difference between the actual Y values from the average. So sigma Y minus Y bar all squared. If we had done Y minus Y bar all squared, you would have seen what we are talking about. So maybe let's do that. This minus okay, it's just this squared, right? This squared. So the summation of that, this is the total variation that we are looking at. Okay, so SST is what? Y minus Y bar all squared. Now, SSE is the difference between the actual and the predicted. The difference between the actual and the predicted. So we have Y minus Y hat all squared. And then SSR is the difference between the predicted and the average. The difference between the predicted and the average. Okay, so as we said, SST is the total sum of squares, and it measures the variation in the Y values around their mean. Okay, variation in Y values around their mean, how the the data varies around their mean, like the standard deviation or the variance, right? SSE is the variation that is attributable to other factors other than the relationship between what X and Y. That's why I said unexplained variation. Okay, the ones that we cannot explain, the ones that are attributed to other factors like size, like the location, like the person who is selling it to you, whether the person is a wicked person or is not a wicked person, like the facilities that are available in the house, and so on and so forth, right? And then we have the SSR, which is the explained variation, which are things or um, the variations that are attributable to the relationship between X and Y. That is that are attributable to the size. Okay, very, very important. All right. Based on this, now this is the last class. So if you've never paid attention, pay attention here, right? Based on this, we are going to calculate what we call the coefficient of determination. Okay, the coefficient of determination. And basically, the coefficient of determination is the what we call the R squared. Okay, you hear a lot about R squared when you grow up. Okay, we coefficient of determination, what we term as the R squared. Okay, is actually the portion of the total variation, which is explained, okay, by the variation in the independent variable. So basically, what portion of the total variation or what portion of the variation is explained by our model or our independent variable? And it is giving us the SSR that we calculate divided by what? The SST. Okay, so what it means also is that I can give you a way to calculate the SST. I can give you maybe the SSE, right? And I can ask you to find the coefficient of variation. Okay, quickly, you can find the SSR by subtracting the SSE from the SST, right? And when you are done, you just divide the SSR by the SST to get the coefficient of determination. Okay, so the coefficient of determination is what we call the R squared. Okay, the R squared. Now, the coefficient of determination is given as this. I think I've already explained that sum of squares is explained by the regression divided by the total sum of squares. And yeah, for the sample, we'll calculate small r squared, and then for the population, it's big R squared if you have a population data, and so on and so forth, right? Okay. Let's see if the R squared has a relationship with a correlation coefficient. Actually, the correlation coefficient is R. So when you square the correlation coefficient for a simple linear regression, you get the R squared. Okay, basically. So what we are going to do is, these are some examples of R squared. If the relationship is a perfect linear relationship, then your R squared is 1. Okay. Now the R squared ranges between 0 and 1. Okay. And the bigger it is, the stronger the relationship and the more fitting the model is. Okay. If R squared is closer to 0, then the weaker the relationship and the less fitting the model you would have. Okay. All right. So those are some of the things that we have. Weaker linear relationship, as you can see. And you can see that it's not all the variations in the model that is explained by X, right? Okay. And here, yeah, we can have a 0 R squared. Okay, we can have a 0 R squared. Now, if you look at the Excel generated outputs, where are you? The Excel generated outputs, you see that there are some summaries here. So we have the correlation coefficient here. Let me just make them, correct them to decimal place, right? So the R squared is what we have here, 0.58, right? That tells you that it explains 58% of the total variation. We can calculate this, okay? We can calculate this, and by way of explanation, we say that about 58.08% of the total variation in the house prices is explained by the variation in the house size. And how do we calculate it? You, from the table, this ANOVA table here, you have the SSR and then the SST. So this value divided by that value gave us the value of the R squared. Okay. Now don't be scared about how we're going to calculate this in exam or whatsoever. By all means, you'll be given enough information to help you calculate whatever value that you are supposed to calculate. Okay. All right. Just be vigilant. That's all. Okay. Now, we have some outputs that help us to determine, to explain more of our results. Okay, we've explained what these coefficients really mean. We've explained what the R square means, right? And this ANOVA test, you would see more about it. It's a test for overall fitness, how the model really fits. But you will learn more about it and in subsequent semesters. But for now, we are more interested in how we calculate the R square. Okay, how we calculate the R square. Okay, so basically, we can use the R square to determine model fitness. Okay, and I would say this: there are some models that have very small R squares, like 20% or 30%, but that model will still be a good fitting model. Okay, but for the purpose of this course, okay, we would use the threshold of 50%. Okay, we're going to use a threshold for 50%. But as I said, practically, you can have smaller house squares, R squares, 20, 30%, 40%. It depends on how well the overall model fitness was done. Okay, but for us, as we are starting, let's stick to an R square of greater than 50%, or yeah, 50% or more. That's what you would do. So when you are doing research methods and then you find out that even smaller values of R squares is being termed as good fitting, and then they use other measures to do it. It's not because your quantity teacher gave you a rat poison or something, but it's just because we want to start slowly and explain things to you, so that as you learn more and what's the word, consume more, you would know how these things are done. Okay, so we are also going to look at one or two things. Another thing that we can measure is the standard deviation, okay, of the variation, which we are of the errors, which we are terming as the standard error of regression. And the standard error of the regression is determined by the square roots of the SSE, okay, which we can determine, we can calculate. Okay, if you don't calculate it, you find a way to get it. Okay, I mean, I would say in an exam or whatever, you would be given a way to calculate it, right? Divided by n. N here is the number, the sample size. K here is the number of independent variables. Okay, the number of independent variables. And here, how many independent variables do you have? We have only one. Okay, and then one. Yeah, so basically it's SSE divided by n minus 2. Okay, all right. Then we'll be able to find the sample size, the standard error. And the standard error helps us to find the standard deviation, okay, of the regression slope. The standard error helps us to define the standard deviation of the regression slope, okay? And the standard deviation of the regression slope is just the standard error divided by the square root of x minus x bar all squared. We need all of this, and this looks like a lot of formulas and a lot of things to grasp, but we need all of this to go through all that we need to do and to get a good understanding of what we need to do. Okay, so in finding the standard deviation of the regression slope, we can estimate it using the standard error, right, that we found divided by the x minus x bar all squared. And that would help us to calculate this standard error we see here in the Excel generated output. And that value we see here, the standard deviation of the of the of the of the regression coefficient. Yeah, if we divide the standard error, yeah, if we divide the standard error of the estimated regression line by the x minus x bar, you're going to get the standard error of the least square slope, that is the regression slope. Okay, so we have these values, and these values help us to make other calculations, and you see what we are doing. Now you expect that for a very well-fitting model, okay, a model that is well fit, you expect a very small standard error. A model that is not so well fit, you expect a very large standard error. So you see this one, the standard error should be large, and here the standard error should be relatively small. Okay, now you fitted your model very good, perfect. Okay, but there are sometimes we need to test whether your model is well fitting. Okay, and you will see this when you are doing more multiple regression analysis. You have to find a way to test whether all your independent variables are good predictors of the dependent variable. I call it, you are testing the predictive power of the of your independent variables. So sometimes you have several independent variables, multiple of them. Okay, the model you turn out looks good. Your R square is good, right? It tells you that generally your model is good, but if you look at how each of the independent variables contributes to the dependent variable, you realize that some of them are good and some of them are not so good. For example, take a typical group work. Okay, you would realize that some people contribute very immensely to the assignment, and then others are just in there, and the only contribution they do is to pay for the printing and the photocopy, and they will be the ones to go and submit the work. Right now, when the results come, you will see that people did well. I mean, you had a very nice score, just because some people, the shark, or no, not the shark, but those who contributed better did a very good a very good work, and then was able to produce a very good report. Okay, and because of that, it has affected those who didn't even do the work. But when we begin to look at individual contributions, okay, to the work, you realize that some didn't contribute. I mean, nothing. I mean, just like that. Their contribution was zero. Theirs was just going to print, going to photocopy, right? Yeah. Um, okay. So we need to test hypotheses about how each of the values, each of the independent variables contributes significantly to predicting the dependent variable. Okay, but here, because you have only one independent variable, that is the only inference that we are going to have. So we are going to test the slope, and we are going to use the hypothesis H naught. That's it, that beta 1, not B1, but beta 1, because we are testing hypothesis about the population. Okay, beta 1 is equal to 0, and then beta 1 is not equal to 0. And if beta 1 is equal to 0, it means that there's no linear relationship, right? If beta 1 is not equal to 0, it means that a linear relationship exists. Okay, so that is what we have. Okay, so the test statistic is basically the difference between B1 from beta 1 divided by the SB1. Remember how we calculated the SB1? Okay, these formulas, and that is why we calculated them, because we're going to use them to test the hypothesis. Okay, so we have the test statistic here. So B1 is the sample regression slope. B2 is the hypothesized slope, and then SB1 is the estimated standard error of the slope. I think I have a battery problem, and okay, we can finish soon. Okay, so these are the things that we will be looking at, and these are the things that we'll be concerned with. All right, so okay, so basically that is what we have: testing hypothesis for B1 and then beta naught. So this actually follows a T distribution. Okay, this follows a T distribution with n minus 2 degrees of freedom. So basically, I'm just going to compare this test statistic with the critical value, and we've done quite a lot about hypothesis testing, critical values, and you can check the other videos on those ones, and then if you've not familiarized yourself with that. Okay, now we have the model that we had about the relation between the house price and then the estimated size. Okay, so we're saying that we're asking ourselves whether the size of the house, does it affect sales price? And I think that from um, the work and the result that we've said, based on the test. Okay, when we calculated our test statistic is 3.329. Okay, based on this formula, all that we've done, and then also our critical value is 2.3. So it tells you that you're going to reject the null hypothesis, and they are going to stick with this. This tells you that there is a sufficient evidence to show that there's a substantial relationship between the house price and then the size of the house. And also, there's evidence to show that the size of the house affects the house price. Okay, the size of the house affects the house price. So if this was less than the critical value, then you would have said otherwise. Okay, all right. Okay, I don't think we would want to look at the confidence interval for now, so we can go we can go beyond that. And there is one thing we didn't do, the p-value approach. You will do that more and more in subsequent semesters. So I will leave that one for you to worry about. But the reason we do the regression also is to be able to predict. Okay, is to be able to do what? To predict. So you should be able to predict a house, okay, the price of the house with an area of 2,000 square feet, okay. And basically what it means is that house price is, we've been able to find the equation of the house price. So all we need to do is just place this, okay, into the regression equation, and then it's done. So 98.25 plus 0.1098x, right? So you put x to be 2,000 in there, and you'll be able to predict the house price. Remember that it's in thousands. So if the size of the house is 2,000 square feet, then your predicted house price is just about $317,000. Okay, so I think that basically that's what we have for as far as regression is concerned. And if there are no questions, we would happily draw the curtain down to regression and finally to UGPS 301. All right, thank you. Any questions?